morning again. Let us start the next lecture. Today we talk about just one subject, which is quantum typicality. I need you to please ask questions during the thing to not let things going further because things will get worse and worse. So ask questions from the beginning. Do you remember that in classical typicality, we use classical typicality, which is the weak typicality, the weak jointly typicality, and the weak conditional typicality in order to prove the theorems by Shannon. We need this to prove. The asymptotic theory, this is called the asymptotic theory of information. Okay, so in the quantum case, we have the asymptotic theory of quantum channel or quantum information theory, which is based on these quantum typicality things. It's the same idea in the classical typicality case, which means that we let the source emit a bunch of information, and then we analyze this using the law of large numbers. But here is a little bit different because we needed, first of all, we needed to, a classical information source, you know what it is. A coin is a classical information source. But quantum information source is a little bit different, so we need to start defining what exactly do we mean by this thing. And although most of the ideas of the classical typicality can be put here, some of them cannot. We have several differences, especially because, do you remember when discussing data compression or Shannon second equality theorem, we say that Bob gets a string that Alice sent to him, and then Bob needs to look at the string and say if that string is typical or not. If the string is typical, then everything is okay and everything works. If the string is atypical, they just declare an error. But looking at a classical string is easy because you can just, look at it without changing it. But look at the quantum source of information. This requires a bunch of care because you look at it, you measure the state. In general, you simply destroy the state when I measure things. Or you can make non-destructive measure, but you can change the state. So this needs to be taken into account in order to define typicality. Otherwise it is this. So we have the idea of gentle measurement. I will define what it is exactly. Gentle measure, in order, this was introduced by Schumacher, that found a way to prove quantum data compression. And then for quantum channels, we have a bunch of different things, but it doesn't work in general. Let us see why, how this works. First of all, what do you mean by quantum information source? Quantum, just remember, a classical information source is just a random variable. Let's just write it here. Do we have a chalk here? Oh, we have a bunch of chalks here. Perfect. I prefer much more this one. Classical information source is just a random variable which has a probability distribution, and so that X belongs to some alphabet. So the thing just keeping emitting the symbols X according to the probability distribution Px. A quantum system is one that randomly attributes quantum states. But quantum states, they do not to be distinguishable. Like these symbols X in classical information source are always distinguishable. All of them, you can perfectly distinguish one from the other. In quantum physics, we cannot do this. If I throw you zero state in the computational basis and a plus state with a superposition, you cannot distinguish these two states perfectly. And the source can simply select one of these. And according to some probability distribution, this probability distribution is classical. So we have a classical probability distribution, but instead of this guy here, we have quantum states. The source just emits quantum states, a bunch of them. So let us think about the basic thing. Alice has a bag of quantum states there, and she just picks up states randomly according to some probability distribution, which is this py here. Okay? And then sends it to Bob. Send the state to Bob. What's the state that Bob with Bob describes the information source. Is this one. It's just the expectation stage, the expected stage. Okay, just take the average over the expectation value of these states over the probability distribution, and it gets this. Remember that these guys need not to be orthogonal. They can be whatever. Okay? But we know that this stage is a quantum stage. It must be a quantum stage. It doesn't matter if it's orthogonal or not. It must be a quantum stage. So it has an spectrum decomposition like this, with this being the eigenstates of rho A, and this is the eigenvalues of rho A. Because rho is a positive and Hermitian operator, we know that these guys unbounded. We know that these guys are just a probability distribution. Okay, that's okay. But then the problem is that the solution actually is that this guy, I cannot distinguish this guy from this guy because of a simple thing. Because we say that the density operators are quantum states, but they are not. Density operators are equivalence classes. A density operator describes an equivalence class of indistinguishable ensembles, which means that I have a density operator here that's written like this, with a different probability distribution, different states, and I have this guy here with the same stage. There is no experiment that let me to distinguish between these two guys. So these are indistinguishable ensembles. Do you agree with this? Okay, this is okay. So that's the thing that helps us. So these guys are equivalent. So I use this guy because these guys are orthogonal, and these guys are the probabilities, are the eigenvalues of the density operator. I simply use this guy that always exists. And then these guys are now distinguishable because they are all orthogonal to each other. So I can perfectly distinguish between these guys. And this implies that the Shannon entropy computed for this state is equal to the von Neumann entropy is equal to the Shannon entropy of the probability distribution. Okay? That's easy to compute in this basis. So now we enter into the asymptotic regime. So we let the source. This is the average state emitted in one single emission of the source. So you see, Alice is picking up a bunch of states there according to this probability distribution. And what gets to Bob is this state. So one state, which is rho. Alice actually doesn't need to send all of them to Bob. But since Bob doesn't know which state she sent, he has to describe the measurements, the statistics, the local statistics by him are described by this guy. There is no, it doesn't matter how many states Alice sent to him. The statistics will be described by this operator here. And then we simply let, as we did in classical case, we simply let the source emit several copies of it. And you see that this is IID hypothesis again. Because these guys are selected according to the same probability distribution here, and then they have the same eigenvalues, and they are independent of each other. So we compose them by tensor products, as we did in the classical physics, where we describe it by Cartesian products of probabilities. Okay? This is okay, so we let the system. And in the end, we take this and go into infinite. This is the asymptotic limit of the thing. Okay, so this is what we call a quantum information source that emits this guy, and Bob is describing the state emitted by this huge thing here. Okay, this is the dimension of this guy increases exponentially with this guy. That's much worse than in case of classical physics that increases linearly with the number of things here. But anyway, we don't need to care about the dimension of this thing. So with this, we can describe the typical subspace. Because what we have is a classical probability distribution of orthogonal, distinguishable states. In the end, that's what we actually have. So we can write an equal sign is missing here. This is equal to this guy. I just rewriting this guy. This guy, every one of these guys can be written like this, a probability distribution. So when I multiply these guys here, what I have is that since all of them are equal, they have the same spectrum decomposition, so they have the same states. What I have is just a huge tensor product of these guys with n elements, and a product of the probabilities, n times the probabilities of each one of these to happen. So it's the same thing as classical physics, but now we have this huge tensor product here. It's this guy, and then the probabilities are just this because of the IID hypothesis. All of them I draw according to the same probability distribution. So it's just a product of this guy, and this is just a shorthand notation for this. Otherwise the equations would be amazing, and the equal sign is missing here. So with this, we define the typical subspace and not the typical set. Because there we have the typical set, the subset of the sequences that are typical. But here we have a subspace where the vector lies, the state vector lies. So the delta typical subspace, which we denote by this guy here, is a subspace of the full Hilbert space of the system, which is huge, is this guy here. That's associated with many copies of the operator. So we let the system to evolve many copies, and this is a problem that we will get in a bit. So this is highly theoretical because we cannot do this in real life like we do in classical physics. I will explain this in a bit. And this guy is expanded by these guys here, like this. And this is a very important thing. This guy is a subspace of the Hilbert space, of this Hilbert space, expanded by these guys. That are all of them orthogonal. Okay? Yeah. Yeah, because these because of these, these guys are orthogonal, so they generate they expand the Hilbert space H. And then we have the tensor product of all of these guys. So these guys span this guy, which means that any vector in this guy can be written as a linear combination of this guy.
And could you define the typical subspace using the original variable y instead of the orthogonal ones?
It's going to be the same, but then you have more vectors here than the number of than the dimension of the vector space. So you have a base that's not orthonormal.
Yeah, but you get the same typical subspace.
You get the same because of this. You cannot distinguish experimentally between this guy and this guy.
Yeah, just wanted to confirm because maybe in some application it could be easier to work with the larger one.
Well, there are applications that we actually use a larger number of vectors, like coherent states. Coherent states is an overcomplete basis. Mm-hmm. They have more. Coherent bases have more elements than the dimension of the space. Mm-hmm. And in quantum optics, it's much easier to deal with coherent state than any other basis.
Yeah.
So sometimes it's useful, but the result must be the same because you cannot distinguish between this guy and this guy. That's the point. But you can. But this is the easiest way to do this. Well, these guys here, any vector in this guy can be written as a linear combination of these vectors, any one. But there is another thing here. This guy belongs to the classical typical set. because this is not a vector space. This is the typical set of sequences. So that's the way we define the typical subspace. We are limiting this guy in such a way that if I draw sequences, because here I'm drawing the symbol X, which doesn't matter where they are distinguishable because of the eigenbases here, and I'm drawing these distinguishable symbols according to this probability distribution. And we know from classical typicality, we know that in the limit, in the asymptotic limit, the sequences that I draw from here will be typical. So the sequences that I get here belongs to this typical set. So there are two things, different things here. This is a vector space, and this is a typical set of classical sequences. Because the way we are defining things. So is that okay? The way
so
define
the
sequences?
typical set of sequences generated by the probabilities P, no?
Yeah, the probabilities P, which are the eigenvalues of the dense operator. Yeah. So we are talking about classical, and why we can do this? Because I can perfectly distinguish between two of these. Any two of these guys. Otherwise, this would not be possible. And then we come back to the answer to the question by Ruben. That will make a little bit difference using P of I, because we have more states than we actually need. But the result is going to be the same. It's just, I think it's more complicated to use this, but sometimes it could be easier, depending on the application that you want. But in this case, I can actually pick up this guy. So we have the typical subspace, which is the quantum analogy of the typical set in the classical physics. And now we needed to define this guy. This guy is the way that Bob has to check if the state emitted by the source is actually typical or not. What do you mean? How can I know that the state is here? Belongs to this space. Because this is much smaller than this guy. So how can I actually know that the state belongs to this guy? I have to project. If it commutes with the projector, then it's there. Oh, did I break it? I didn't touch the microphone. I didn't touch the microphone.
No, you have to start again from the beginning.
For the beginning, yeah. So in classical physics, you just say, look, Bob, look at the sequence and see if it's typical or not. Here we need to say the same thing, but what does we mean? What does this mean? Looking at the quantum state. Yeah, who knows? We have to define projectors, and then they realize that if I simply project the system and do measurements on the system, I will usually destroy the system or change too much of the state. So this is a huge stage. It's a huge subspace because this is a tensor product of, in the asymptotic limit, infinitely many states. So this is very huge. The information that you get here is huge, like the information that you get in a huge sequence. But we can define a projector like this, which is just the projectors defined by this sum of projectors, in such a way that we're summing over the typical set of classical sequences, drawn according to the probability distribution defined by the dense operator, the eigenvalues of the dense operator. So this is a projector onto this guy here. And we have the other projector, the complementary one, that's the identity in the entire Hilbert space minus this guy. So if we apply this measure to the system, I will get 1 bit of information. Just 1 bit. Because the question that this projector answers is the state in the typical set or not? This is just one bit of information. And we have plenty of bits of information in the state because it's huge. So we are assuming that we are disturbing just a little bit the system, because we are getting just one bit of information of many bits that you have there. So we can assume that the state doesn't change too much. That's the meaning of gentle measurements defined by Schumacher. Is that clear? Okay, because we just, get one bit of information. So that's the way Bob actually tests if the state that he got belongs to the typical set or not. Ask, Remy.
No, it's not a question.
Yeah.
It's not a question. Just realize that I can use this for something. So good.
For something,
Thank
for
you.
something what?
Some.
In your work. Oh, that's good. Then it's worth. That's a good thing. That's why we are here, actually. So, then the measurement in the subspace. The measurement does like this, okay? Because we needed to define how Bob checks this thing. He needs to check if the state belongs to the typical set or not. For some state here that belongs to the entire Hilbert space, that was supposed to be emitted by the source, this is a measurement that put in the classical register one bit of information. This is the state of the classical register, it's just a qubit. And if it doesn't belong to the guy, then the state of the classical register is 0. If it does belong to the typical set, the state is 1. And there is one more thing. We expected from typicality arguments that the probability of the state being the classical in the typical subset approaches 1. So if the probability approaches 1, this guy will commute with this guy. And the state will not be disturbed. Because the source will emit state that belongs to the typical set in general. So the density operator emitted by the source will commute with the projector into the subspace, into the typical subspace. This we expected to occur from typicality arguments. And this actually occurs. We prove this, that this actually occurs. But we needed to do these measurements, all of these. In classical physics, in classical information theory, we didn't mention this because looking at the sequence is a clear thing that we can do without changing the sequence. We just look at it, is it compute the sample entropy and say, this is equal to the entropy of the source, and then it's typical. But here we cannot do this. That's the way we look at the system, without perturbing it too much. By just extracting one bit of information by this guy, and we expected that as the size of the system then go to infinite, the probability of this guy to be in the typical set is 1, converges to 1. So in this limit, this guy will not disturb the system, because the system will always be in that typical set. And this operator will commute with the density operator of the system. Okay? Is this, okay, this argument? Perfect. Then that's the measurement. But this is theoretical, because how do we do this? So we needed to have access to a bunch of, let us think about qubits. I think the source is emitting, those states are qubits. So, the measurement. We needed to have access. Do you remember the plot that I showed you yesterday? To really have a convergence of the sequences, of the classical sequence emitted by the source, to belong to the typical set, which is the condition that we have here, to define the typical subspace. We needed that this sequence should belong to the classical set. We needed millions of bits emitted. So we would have, in order to implement these things, we need access to millions of qubits, coherently manipulating millions of qubits in order to implement these measurements. This is not possible. At least not now. I mean, so this makes this quantum channel theory highly theoretical, because we simply cannot implement this protocol. It's too difficult, and these operations must be noiseless, which is even worse.
But can you not individually prepare these states? I think they are not entangled between each other, right? So it's like a product.
They are not entangled, but the problem is that if you measure each one of them, you are not implementing this measure. You are getting many bits of information. If you measure any one of them, you get any bits of information, and then it's over.
Yeah, I mean, in the end, you would know then the exact state, right? And then you could say
I'm not saying that you know the state. I'm just saying that actually, if you just perform one measurement in each qubit, you don't know the state of the system. But you get any bits of information from this measurement, which means that you got a bunch of information from the state, from the total state, which means that you perturb it too much in the state. The state is completely different. Then you cannot do anything with them. The introduction of this guy is because in the asymptotically limited, you don't change the state.
Oh, yeah.
So I cannot measure them individually. In classical physics, we look at every bit of the sequence and compute the sample entropy. But here we cannot, because we changed the state of the system, that's it. And you need to perform these.
I thought about
these measures should be non-destructive. Because, I mean, you got the state, and then you see, this state belongs to the typical subspace. Then let's just do our process that we want, a computation or whatever we want to do with the state. So we cannot destruct the state. And we have to guarantee that the state is the same after this process. Otherwise, our computation will not work. That's the difficulty in doing this thing. And that's why this is, highly theoretical thing, because to implement this thing, we need millions of qubits, being coherent and controlled. And this is, we simply cannot do this. If you could do this, we could do error correction in quantum computers, and that would be amazing. We could compute whatever we want. So, but even though theoretically this works, mathematically it's very nice, and we can use these things, but this means that you cannot achieve Schumacher's compression. We simply cannot do this. We know that theoretically it's there. You can compress quantum information, but we cannot achieve that thing experimentally because we cannot implement these guys. And to achieve Schumacher compression, we need to do this. The same way we needed to check if the classical sequence belongs to the typical set or not. But this is easy, we can do this. But here we cannot. So that's just a thing that is a huge difference between the quantum and the classical compression, data compression.
But is this true? Because this is a so there is no single protocol to achieve Schumacher compression, no? Maybe
experimentally no. Theoretically, yes.
So maybe the
protocol is this.
Maybe there are other protocols, local protocols, that they can allow you to asymptotically approach to Schumacher compression.
Theoretically, yes. Yeah, theoretically we have a protocol that can in channel also, but we cannot do. I cannot achieve this even in classical physics because we have to find which code actually achieves that thing, and this is difficult. When you go the asymptotic limit, that's hard. Which is the best code? But in principle, we can do in classical physics, but in principle, we cannot do here, even in principle, because you cannot implement this thing. At least for now. But as one thing. One thing is that we cannot do because of technological limitations, and not the limitation of the theory. The theory doesn't limit us to do this. It's our technology that doesn't allow us to do this. So that's a side thing. Yeah. So the properties of the typical subspace. That's easy. It's easy to prove. The proofs of these properties relies exactly on the same basis of the classical property that we proved last week. It's basically the same thing, unity probability. So that's what I told you. The probability of the emitted state by the source to be in this typical subset, it converges to 1 in the asymptotic limit. The same way that you have the probability there of the sequence to be in the typical set converges to 1 in the classical case. Here is it means that to measure this guy is closer to 1 than this guy belongs to the typical subspace. And the proof is, it follows the same line of the classical thing that we proved last week. You see that the equations are the same, actually. The equations are exactly the same. Exponentially small cardinality. What's the cardinality of the typical set? Is the trace of this guy. That's the size of the typical set. The trace of the projector gives you the size of the subspace. Not the typical sets or the typical subspace. So just compute the trace of this guy. Let's call it volume or size of the subspace that you are projecting. And then you can bound these using von Neumann entropy. That's von Neumann entropy of the stage. This C is a constant. That's not huge. That's order unity. That it changes according to it. You use the weak or the strong typicality definitions. But this number is arbitrary. This delta number is arbitrary. So you don't need to care about this C constant. The problem is that this n is very huge. This delta is arbitrary. This epsilon is arbitrary, but belongs between 0 and 1. It's in the interval of 0 and 1. So the size of the subset is limited by this thing. You see that if you have a source that emits sequences with a uniform probability distribution, then this guy is going to be the log of the size of is going to be the cardinality of the log of the cardinality of the space, and you cannot compress anything. That's the idea. This guy is going to be the same dimension of the entire Hilbert space. This is the same thing that happens there when you have a uniform probability distribution and the size of the typical set is equal to the size of the total set of sequence. That's the same thing. So the notion of typicality here is exactly the same. The other ones change, the jointly and the conditional change, but the notion of this typicality is exactly the same. We just changed the thing. What's this? Oh, a fly. And this is the last one, that's the partition. You have to prove, the proof is exactly the same, but of course, you have operators here. That's the classical thing. That's the classical equipartition property, which means that the probability of the source to emit a sequence that belongs to the typical set is bounded from above and from below like this, by the Shannon entropy here. Here, this is an operator inequality, but this is a statement about the eigenvalues of this guy. The eigenvalues of this operator, which is just the probability distribution. That's why this equation is equivalent to this equation in the asymptotic limit. Can you see this? Because in the asymptotic limit you have unity probability, this guy commutes with this guy. So this guy and the rho and the pi have the same eigenvectors in this limit. And the eigenvalues of this guy, the rho, are just the probability distribution. So this equation in the asymptotic limit is equivalent to this one. Can you see this? We can discuss this. But it's based on this property here. So this property means that this guy commutes with this guy. And then in the asymptotic limit, they commute. And then these guys have the same eigenvectors. And then this is exactly the same as this equation here because these are the eigenvalues of this guy. So these equations are equivalent. But this is the asymptotic equipartition property, which means that every eigenvector here in this space has the same probability. So every eigenvector inside of this subspace, which is huge, by the way, but they have the same probability of being populated, let us say like this. And always this guy happens because of the asymptotic, the classical property. And one thing that we can prove is this last equation. This is the Tracy norm that we defined yesterday. Yesterday? Yeah. No, the day before. The day before yesterday. So the difference in the asymptotic limit, the difference between the rho A, which is the state emitted by the guy, and this guy is just, this guy is here. It's this guy in the middle. Okay, the difference of this guy in the asymptotic limit is bounded by this guy. Epsilon is a small number, positive small number. So it means that this guy converges to this guy in probability in the asymptotic limit.
So if I understand, what you mean is that for every epsilon there exists an n such that
exactly.
This is a...
Exactly. This bound is respected, and this is the basis of Schumacher compression. Because Schumacher, you can prove that because of this probability, you have a much smaller set of density operators that will be emitted. You don't need to code the entire Hilbert space of the system, but you just need to encode the states that are in the typical set here, in the typical subspace, sorry. And you guarantee that when you go to the asymptotic limit, for every epsilon, like Mikkel said, between 0 and 1, there is an n that satisfies this inequality. So Schumacher compression says you compress this guy because this is the state of the system. Because this is the state after you check if the state belongs or not to the typical subspace. You see? Mm-hmm. That's the state that we have after this operation. So let us suppose that Alice is communicating with me some state that I need to use this one.
Yes.
That I need to use in order to do some computation, to put in a quantum computer. I don't know. And then I need this guy. I need rho A. But then we do it. Alice sent me a bunch of copies of this guy that in the asymptotic limit, I have to check if these guys belong to the typical set, to the typical subspace. So I project the guy here and get this state. If the probability of this state is getting closer to 1, this guy will be very close to this guy, because I'm just getting 1 bit of information from this thing. And actually, you can prove that this happens. So if this is happening, and I make the computation with this guy instead of the real one because I project the guy, so I change it. I have rho tilde in my hands, not rho. And then this will be the error that I will be committing in the computation. He has a...
Yeah, my question is, first, so that rho tilde, the one that is projected, for that equation, are you normalizing it afterwards, or you are taking it without normalization?
Oh, no, sorry. No, you normalize. You normalize by the trace of...
You normalize,
I don't know, of course.
Okay.
Everything is normalized there.
Okay, and then I understand.
Actually, I will put this in the slide because, yeah, of course, if this is not normalized, this is normalized, then this equation will not be valid. Yeah, if this is not normalized, then this equation will not be valid. Yeah, of course, it changes, but anyway, it's normalized.
Okay, and then I understand that the square root appears, I mean, that epsilon can be related with the epsilon that you got in the probability statement, in the unity probability
It's the
statement,
same,
right?
it's the same one.
Why do you get a square root?
Well, in the proof, because this guy involves the square root. You do remember the definition of this guy? It involves the square root of the guys inside the key. So this epsilon comes from the proof of this equation. You just compute this guy, and then you prove an upper bound on this guy,
Yeah.
and the upper bound appears the square root because there is a square root here.
Yeah.
This guy is defined as the square root of the
But
key.
I mean, I understand that square root is appearing because you are normalizing the second state, right?
Well,
If
but
without the
normalize it by the
normalization,
trace of this guy. You
Yeah.
just take the trace of this guy,
yeah,
which is a probability. So you normalize it by the probability.
yes. What I mean is that if you were not normalizing, then this difference would be just smaller than epsilon, right? Because the only difference between the unnormalized version is the part that is not in the typical set, and the probability to be there is smaller than epsilon. So then,
Wait a minute. I don't think I follow your question, because I mean this guy is in the typical set.
yeah. But the one in the left has
This-
a small probability to be out of the typical set.
Yes.
So if we measure that, the complement of the typical set, we could try to distinguish between those two. And we are there with probability epsilon. So with probability smaller than epsilon.
Well,
So the trace.
I think I got a question. The measurement that you do is this one.
Yeah.
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 This one. So if you get this guy 0, you just throw away. You don't proceed. You declare, no, I got an error because the system is a atypical set. And then you come back from
Okay.
scratch.
Yeah, okay. I mean, I will just see where the square root appears and it's.
Oh,
fine.
the square root appears during the proof because of the square root of the trace norm. It's defined as a trace norm, so it appears there. But anyway, for this equation, this normalizes in the sense that the trace of this guy is 1. That's what I mean by normalization. And then I'm assuming that the process get correct. So you got Bob got 1 as an output of his measurement, and then the new state that he has is this one. And then he performs the computation of this guy instead of this guy, and everything is going to be the same. I mean, it's because of this boundary here. So that's why things works in the asymptotic limit.
Yeah, I had the same question about the normalization, but yeah, it's already.
So is it clear? Because
Yeah.
I mean, we can discuss this.
No. I mean, now it's clear.
Okay.
I mean-
Okay. So that's why Schumacher compression actually works in the asymptotic limit. The problem, as I told you, is how to get to this guy, because we cannot perform that measurement on the system, so we cannot actually check if the state is or isn't in the typical subspace. But if we believe the theory, it will be with high probability. And I mean, we believe the theory because the theory is nice. And I like nice theories. Okay, these are the same properties that you have in the classical subspace, but then things change a lot when you go to multipartite systems. Change a lot. Let us think about the case of bipartite system, which is the easiest one that we have. So, remember that the way we define a joint typicality yesterday? We defined it in the way that the sample entropy of the joint sequence approaches the true joint entropy of the surface. And the sample entropy of the marginal sequences approaches the entropy of the source, the marginal sources. This means that this joint sequence is typical, and each marginal sequence is also typical. So that's we impose. So, but then comes the problem. Because I need to check, in order to determine if this guy is typical or not, I have to apply that projector on the typical subspace. This changes the stage. Here is a little bit worse because in order to determine if this sequence is typical, so I can define a joint measurement on these guys and simply measure them. Okay, this is okay. And then I realize, oh, this is typical or not. But then how I can do this? I can check this marginal and this marginal and see if they are typical. But I can do the opposite. I can do first these marginals and then the joint. And these guys need not commute. If they don't commute, this measurement, the state will be different at the end. And I cannot proceed with the computation because I simply don't know what state I have. And I change the state a lot. So the state can be whatever. Is that clear? Because this implies that we don't have joint typicality in general in quantum physics. Because the measurements here to determine if the sequences are typical or not doesn't commute. The measurements don't commute. In general. We define a case in which they commute, so this is but just a simple case. But in general, we cannot define a joint probability distribution. Joint typicality in quantum system because measurements in quantum mechanics don't commute in general. So we don't have this thing, but we do have a very, very, very special case in which this actually works. Let us consider this stage. So we just, keep defining joint typicality the same way we define typicality. I can define the stage emitted by the source, which is this one. That is just a classical variable there. And I always can, this can always be written. It's just the decomposition of the operator into its eigenbase. That can always be done. And then I can always write this, which is just a product of any of these same guys. And then I define a typicality in the same way, that this is the typical joint subspace, bipartite subspace, and this sequence belongs to this guy, to the typical set of Z. So this is exactly the same thing. It just changes Z by X and AB by C, and I have the same thing. The same thing as before. This can be done, and then I define the typical projector. There is no difference between these guys. But the commutation problem still exists between A and B. And we cannot actually certify. We can certify that this Z belongs to the typical set. But then we cannot certify that the marginals also belong. So we don't know if they are in the joint typical set. But this is perfectly fine because it's exactly the same thing we just did. I just, call it what was being called A there, now it's AB. But it's the same thing. It's just a name that I'm doing this. But there is a way in which we can actually do this, that the measurements commute and everything is okay. Is the way for these class of states, which are called classical states. Because these guys, this is a joint probability distribution. This is an orthonormal basis in the A subspace. This is another orthonormal basis in the B subspace. So this guy here has only classical correlations. It's not entangled. It has no quantum correlations at all. So in this case, I actually can do everything in the same way I do. So I can define joint typicality in this case, but just in this case. If these guys has quantum correlation, then it's over. There is no way. The only way is that these guys orthonormal basis here and this guy's orthonormal basis here. But this implies that this has only classical correlations. If a state has quantum correlations, they cannot be written like this. It's impossible. So,
but I have a very stupid question because correlations depends on the basis, no?
Well,
so-
in these bases, no? Correlations in these bases,
No, that depends on the basis. I mean, you can always go to a basis in which they are not correlated. So it's possible
Wait a minute.
by a global unitary.
Well, by global unitaries, you can destroy correlations actually.
Yes.
But yeah, but no. I mean, if Alice, let us start that I start with a tensor product of states, so we have no correlations. What correlations can I create by acting locally on the states? I can only act locally and classically communicate. This is the best you can do. You cannot do better than this.
No, but what I mean is,
you can do a little bit different, but entanglement you cannot create here.
yes, but this was not my question. Actually I didn't ask the question. So what I mean is that if you can so you want to define typicality in these kind of systems, no?
Yeah.
Why is not possible? So why is typicality dependent on the basis in which you are working?
Because of these. I mean, we have this measurement problem because these guys don't commute. So the only way to define typicality is for these special classes of states where both Alice and Bob cannot do global operations. Because then if they can do these, they can create entanglement and everything else. But this is a very special class of states in which we can define a notion of joint typicality. But if we can create more states, then there's not. We cannot define these things. I mean, I'm thinking about a quantum source, quantum information source that can emit only these sort of states. It cannot emit any other state. Okay. But correlations actually they don't depend on the basis, no? Because correlations correlations are computed as entropies, which are traces. So coherences does depend on the basis, but correlations not. Correlations are traces, and traces are invariant under local unitary transformation. Of course, I can destroy correlations doing global things, but this is a different thing. But if I change the basis locally, here and here, you cannot change correlations. You cannot change it. There is no way to do this. Yeah. So from these, I can simply construct any copies of these with the same notation as before. This is the tensor product of any of these guys, each one of them. This is the Cartesian product of the joint probabilities of everybody. This is the same thing. And then I can simply define the joint subspace exactly in the same way. But now these guys belong to the typical sequence. And because this is a classical probability distribution, I know that this guy, which is the marginal, the probability distribution of Px and X, I know that this guy is such a way that this guy belongs to the typical set of X. We know this. And the same thing happened with Y. So we know that we fix the conditions of joint typicality in classical physics, because in classical typicality actually. And these guys spans this subspace. And then we have the joint typical projector. That's just this one, just projected this guy here and this guy here in the typical sequence. So in this case, I can define exactly the same way. But in other cases, we simply cannot define this thing. Okay, is that okay? Make it. Not at all. No, we can ask, we have time. It's noon. No, 10 to noon. Yes, okay.
The last two sums, they should sum over the typical subspace, the jointly typical.
Oh, sorry. Yes.
Or
Exactly. No, yeah. They span just these guys here. No? Yeah. So Thank you. I will fix the 3 typos now. I'm missing quality sign, the normalization of the dense operator. That's you to introduce the and these is the okay. Thanks, Mark. That's the last thing that we to define, and this is the most complicated one, actually. But we can define this. That's nice. The nice thing is that we can actually define this, and we needed this to study the channel quantum channel capacities. Because if you remember channel capacity, we needed conditional typicality. Otherwise, Bob would be unable to decode the information that's getting out of the channel. So we needed to define joint conditional typicality to do this. Here is the same thing, because the channel, the quantum channel, the classical channel, they are defined by conditional probability distribution. We have an input and we have an output, and we want to know how correlated the output is with the input, because from the output I want to know the input. That's the basic thing of communication. So it's a conditional probability distribution. So we need conditional typicality in order to correctly decode things in the asymptotic limit. So let us consider random variable. This is a classical random variable. And the quantum system with orthonormal sets. These guys. So we have a random variable and a quantum system there, with this basis defined for them. And these guys, I use it to represent the outcomes of these guys. Okay, the alphabet of the random variable. So since they form an orthonormal basis, I can perfectly distinguish between all of them, like in the classical system. That's okay. That's the Alice thing. So we generated one realization of X. Just pick up one X there. And then we generate a random quantum state according to this X. We generated many of them according to some probability distribution, but conditioned to this X. So we have a probability that's Py that conditional to X. And from this Y, this probability, this is a probability, I generate a bunch of states. Okay? Okay, so this procedure gives me a set of the size of this guy, because I have one set of for each one of these outcomes of quantum information sources. So you see now I don't have one, I have a bunch of them. Okay? And the expected value is this guy. So it's conditional to the value of the classical variable. And I have rho B because of Bob. And these are the conditional quantum information sources. Okay? The same way. So, what I have is that what is called a classical quantum ensemble. Because the classical thing comes from the probability distribution that I'm generating here, the conditioning thing. And then this is the state of the classical system there, the classical register. And this is the conditional state, the conditional quantum state, conditional to develop this guy. So that's the ensemble that I have. And then from this I can build this, the expected density operator, that will be the output of the channel, which is just this guy. X, B is this guy here. Okay, the same way we did before. And then we can compute the entropy of this guy easily. The channel phonome entropy of this guy, the phonome conditional entropy of this guy, because I'm conditioning on the state of this guy. Okay. By defining this guy as the eigenvectors and eigenvalues of the conditional operator, as just, write the spectrum decomposition of the dense operator, the probabilities will be conditional, because for each value of X, I can be a different set of these guys. That's why you have the X here, because X can change this base, can change the operators. So for every value of X, I will have a different set here. And that's why you have conditional probability distribution in the decomposition. So these are the eigenvalues of the state, and these are the probability and the eigenvectors of the density operator, and these are the eigenvalues of the density operator. Okay? And then with this I can compute the conditional entropy in terms of these probabilities. So asymptotic limit, again. Asymptotic limit, you just pick up this guy, multiply this guy n times, and use the same, exactly the same notation, except for this guy means this one. So it's a huge tensor product for everybody. For every value of x, I have a different density operator here, and I have a different basis here. That's why we have the x labeling these guys here. They can be different. And the conditional probability. So we can define the weak conditional typical set in the same way, because the other variable is classical. So I already measured the guy, so it's classical, I have everything, but I needed to pick up this guy. And conditional typical subspaces with this small x here. Let me be careful if I did a mistake. This is a small, this is a small, yeah. Yeah, no typos here, no typos here. So this guy is a conditional subspace conditional to this sequence associated to the specific sequence. This sequence is a realization of the big random of the big X, no? This sequence is a realization of this guy, of this random variable. It's a classical one that we have there. So this is the conditional typical subset, which is spanned by these guys, associated with these, which are the density, the eigenstates of the density operator, associated with this specific sequence. So, and then I just define the way we define typicality, the sample entropy of the outcome of the sequence, that outcome is this thing, conditional to the sample to the sequence that the input must approach the true conditional entropy of the source. That's the way we define typicality. Okay, that's the way we have the typical subspace conditional to a specific sequence. Okay, exactly the same way we did before. And then we define the projector. And the projector here is correctly summing inside of this subspace, the output subspace. Okay, this is for making the measurement to test if the state is indeed a typical one or not. To see if things working. Properties starts to think to be a little bit different. Let me check it. Big, no typos, no typos. Yeah, these are all big X's here. Because the unity probability, I cannot say things about specific sequences, but I can say things about the average expectation. Which means that, well, the sequence will be in some of the typical sets, in some of the conditional typical sets. On average, that's why I cannot say, oh, these will be here, exactly here. No, I can say on average they will be in one of these typical subsets. To say exactly which one we needed to actually to project this thing every time, which is worst. So we just take exactly the same way we did in the classical conditional typicality. We average over all possible probability distributions, not the input, which means that Alice can change her probability distribution the way she wants. We average over everything, and we assume that Bob doesn't know, absolutely has no knowledge about what Alice is doing there. Okay, and then this is the representation of this big density operator for all the all the possible realizations of the classical variable. And then it's possible to prove this relation exactly following the same line as the classical conditional typicality. This is a nice thing actually, because the proofs are not that different. You just take care that you are dealing with operators instead of numbers, and the proof follows. This guy, exponentially smaller dimension. You prove that's exactly the same thing that you have there in classical typicality. So it's exponentially smaller than the dimension of the entire Hilbert space. That huge product of the Hilbert space that you have there. And the other way, I mean, this is upper bounded by this guy, and the same thing happened in classical typicality. To lower bound this guy, you needed to average over all the input probability distributions. So you needed to compute this expectation value of this guy here. So it's the expected lower bound of this guy. You raise your feet. Oh, okay. But you don't have a question? Yeah. Oh, okay. So it's the same thing. We can bound the average, but not the real quantity. But that's okay. It's a good bound. This is a very good bound, especially when n goes to infinite. Then this becomes excellent. Okay, and the last property, equipartition, which is exactly the same statement that we did before, but we project, instead of projecting into the typical subspace, we projected it into the conditional typical subspace. So the measurement is 1 minus this guy times 0, 0, plus this guy times 0, 0, 1, 1. That's the measurement that we are doing. Instead of the big projector, we just put the projectors in each one of the subspaces. And this shows that the eigenvectors of these guys are equally distributed. So this is basically a statement, since these guys share the same eigenvectors in this limited, so this implies that the conditional probabilities here are equally distributed inside of this space. So that's why the name is equipartition theorem here. That's the equipartition property. So this we use it to prove several properties of the channel communication. Classical communication, we just have one thing, that's the channel capacity. Or channel capacity, or classical channel capacity, or whatever. In quantum physics, we have several of them. We have the quantum capacity of classical information, which is classical information over a quantum channel. I can send quantum information over a quantum channel. I can send classical quantum information over a classical quantum channel with a measurement. If you think a measurement, what actually does? It has a quantum state there. We apply a measurement, and it transforms quantum information into classical information, a string of bits. So this is a quantum classical channel that has its own capacity also. So we have several of these guys, and these are related, all of them are related with the mutual information between these guys, between the input and output. Because this is what we want in the end. And the quantum capacity is the maximum of that thing that we defined 2 days ago that we call coherent information. That's the quantum capacity of a quantum channel. Then you prove using these probabilities, except the joint typicality, because it doesn't hold in this case. But the rest we can prove in the same way. Guys, that it was I planned today. Yeah, it's 1 hour, more than 1 hour actually, because this topic is quite a little bit difficult, so I didn't bring anything else. Let us make it, this low, because this is, you see, this is hard to properly understand these things. It's quite abstract. Yeah, that's it. Questions, please. We do have time for questions before the queue gets really huge. Yes, Mike.
Yeah, I think this unit probability theorem for the conditional typical subspace. Yeah, I mean, you cannot do this for one particular instance of X, or I mean, you said
Do me
like
one if I
yeah,
just replace this guy by a small x
yes,
and this guy by a
without-
small x. No,
without
you
taking
cannot prove
the
this.
average.
You need to
over
average,
X.
otherwise you cannot prove this. That's needed also in classical typicality.
Okay, so this is also
Because
in the classical case.
otherwise this will become dependent on the probability of input, and this is a thing that you don't know.
Okay.
I mean, you simply
Yeah.
don't know what's being inputted in the system. If you know this, you don't need to communicate because you already get the information. So Alice doesn't need to send anything to you because you already know the thing. The problem is that you don't know, and then to prove this, you need to average over all the input probabilities, both in classical cases and also in quantum cases. Well, this is.
But I mean,
These are probabilities also, a conditional probability.
yeah, but
The
I
trace
mean,
here,
in
so-
principle, you could probably calculate this and would find something similar, maybe, if you just take a particular sequence, small xn. You could calculate.
But then this guy here would depend on the sequence.
Yeah, but I mean, it would be more or less the same.
No.
Probability or not?
It's different because you have a explicit dependence here on the sequencing. So you have to average to eliminate the boundary, because if you have a boundary that depends on the thing that is being inputted, the boundary is not very useful.
Yeah, but maybe you can find then somehow another bound so that you get rid of this
Average?
dependence, or I mean, in principle, the bound can depend on the sequence, but maybe with some tricks you could show an even.
I don't know if this is possible. Maybe for some specific application, you can let the boundary to depend on the sequence, but it's a very specific application. But in general, you want a boundary that doesn't depend on the input. So you have to average. This happened also in classical typicality. If you remember the classical typicality thing, we have the same boundary here, the same average here, and also here. And we don't have here because of the conditional probabilities asymmetric. You are conditioning in a classical variable, you average over these conditionals only, and not on the output. But if you don't compute this average, you cannot prove the bound. Maybe you can prove some bound that will be dependent on the sequence.
Okay.
But I don't see how this can be useful actually. Because then, imagine that this epsilon here is a function of the sequence. And then I want to know how good my protocol is. To compute this, I need to know the sequence. But if I know the sequence, I don't need to know how good the protocol is because I don't need the protocol. I know exactly which state I have.
Yeah. No, I see.
Yeah, the conditional typicality is the most
yeah.
difficult one to understand.
But
Even
I mean,
classical
one wouldn't
quantum-
expect that there exists a sequence that is a big outlier from the average. That's like my point. I mean, on average, we have this
This thing, yes.
inequality that most of Yeah. But I mean, I was just thinking maybe there exist some outliers which behave really differently.
Well,
But,
it's not very different because one thing you must have in mind: every sequence that you have here, every action that belongs to this random variable, they belong to the typical set of the random variable. So they are restricted.
yeah, yeah.
So everybody here belongs to some typical set. I mean, the state
Yeah,
belongs
yeah.
to the typical subspace, and the random variable belongs to the typical set.
Yep. Yeah, okay. But if I take now an xn which doesn't belong to the typical subset, then for these guys,
then it's highly probable that the density operator will be outside the typical subspace. And then the communication process will fail because you cannot, you apply the measurement. You see, no, it does belong to the typical subspace. Stop the thing, start again.
yeah,
So that's why it's difficult to run this thing, because you need to check, you need to perform that measurement. Otherwise, you actually don't know.
yeah,
But we believe that the probability is good, and then we keep doing things, and the error is the error. It's the best we can do. But it's very nice in the end how things works when you go to the infinite limiting. I mean, it's much easier to do things, and one of the things is it's much easier to bound the averages than to bound the probability. So if you're facing some problem in quantum algorithms, quantum computation, or quantum whatever, try to use the tools of probability. That we have several inequalities in probability theory, like the one used by Shannon's Markov inequality, that bounds averages of probabilities. We have a bunch of these, and these can be very useful for us to bound actual probabilities. And this was what Shannon did actually, and this is very useful too. And the thing that Davies, you tried to use it to solve a problem that Mikkel proposed. Maybe we need to bound probabilities, but we don't know how to do this. Let us bound averages and see what comes out from this thing. More questions? Okay, I'll be here all day long, so